Hello, my name is Mara. I'm from Environmental Solutions at North Dakota State University in Fargo. Due to some busy summer schedules, the rest of the team won't be presenting with me, but other team members include Ariana, our project manager, Tyrell, our project engineer, and then Erica and Tyler were the other design engineers on the project. Our project was treatment and disposal of biosolids from wastewater lagoons in West Fargo, North Dakota. A little bit of background. West Fargo has a population of about 35,000 and is continuing to grow every year. And because of that, they've decided to decommission their wastewater lagoons, and Fargo is regionalizing their wastewater treatment facility, which is allowing for that. Odors have been an issue from the lagoons in the past, so that was something we had to keep in mind when we were doing our project. Our problem was to dispose of about 660,000 cubic yards of biosolids. We were given a 10-year timeline and the instructions that the land will be used for commercial or residential development after the decommissioning. So that took away a couple of our options, like just leaving it as is or simply covering it with dirt or other fill. So first we came up with some alternatives to this problem. The 5 alternatives that we narrowed it down to were land application, landfill use, incineration, heat dry and sales, and composting. I'll talk about these alternatives in depth a little bit more in just a second. So the first alternative is the simplest, land application. So no thickening or dewatering prior to applying it to the land is necessary, and there is an abundance of agricultural land available in the area. We estimated approximately 150,000 acres within a 10-mile radius. Basically, all that needs to be done is hauling the biosolids to the farmland and applying it, but special equipment would need to be purchased, and there is a limited window of application due to harvesting and planting seasons as well as the weather. Our second alternative would be landfill. So for this alternative, the sludge would be dewatered using sludge drying beds to reduce the volume. The volume would be reduced by approximately 25% if we used this alternative. The biosolids would then be hauled to the landfill to be used as daily cover. So we wouldn't just be disposing of them at the landfill, they would be put to some good use. The third alternative is incineration. So again, the biosolids would need to be dewatered for this alternative, and a belt filter press would be used. Now, the city of Fargo already has a belt filter press system at their wastewater treatment facility, so that technology would be utilized for this alternative. The incineration technology that's going to be used is a fluidized bed furnace. In that process, bottom ash and fly ash are produced. Bottom ash has no beneficial use, it just needs to be taken to the landfill. But the fly ash can be called and used as a substitute for Portland cement or in FDG gypsum. Our fourth alternative would be heat drying and sales. Again, dewatering would be necessary because 25% solids is needed for the heat drying technology to be effective. And the belt filter press in Fargo would be used for this alternative as well. Indirect dryers are going to be used for the heat drying technology due to the reduced odors. And the end product is marketable, so it can be sold as fertilizer, and it's pretty much just small pellets. Nothing too fancy there. The last alternative we considered was composting. We would use in-vessel composting, so basically just a big silo. The benefits of using in-vessel are that there's less odors produced and it can be used year-round, even when it gets pretty chilly here in North Dakota. It has to be mixed with a green component, so wood chips, grass, something like that. So we would need to come up with a source for enough green component to our compost mixture. And again, the end product is going to be marketable. And then unlike alternative one, it could be used for domestic or agricultural purposes because it'll be treated to a higher standard than just land application. We also did a comparison level cost estimate for our alternative analysis. And you can see that as the technologies get more advanced and there's more involved in the treatment process, the more the price increases. So the first two alternatives are fairly simple, fairly straightforward, and therefore have a lower price. Our alternative analysis was a three-tiered system. Each criteria was split into one of 5 categories and given a primary rank, so a score of 1 to 5, and that rank was based on how significant it was to the process. A secondary rank was given to each criteria in the categories, so those 5 different categories I mentioned above, based on their significance, and all of those, when you sum them up, equal 10 to avoid any one category having too much influence on the analysis. And then each of our team members scored all alternatives on a scale of 1 to 5. Hopefully this makes a little bit more sense after the next slide. So here's just an example of one of our categories. This happens to be the most important, which was public acceptance. You can see all of the scores here are multiplied by 5. And then let's take odor, for example. It is very important to the city of West Fargo, so we gave it a secondary rank of 4. And then we just had a brief explanation of what that criteria meant to us, so everybody was on the same page when they were doing our scoring. So the overall scores for each alternatives were determined by summing every criteria score, and every criteria score was figured out by multiplying the primary rank, the secondary rank, and the average score of all of our team members. And for our alternatives, you can see that land application followed by landfill were the top 2, and heat drying and composting were the bottom 2. Our recommended alternative actually isn't our highest scoring alternative, and that is because we initially started designing for that alternative and realized that there is a lot more that goes into planning for that land, and there's just too much variability for our 10-year timeline to depend on all that land being available when we need it. So we did our design for the second highest alternative, and that would be to take the biosolids to the landfill. Before we started our design, we came up with our basis for design. I'm just going to point out a couple important things here. We will be running our process 180 days a year, so about half the year. The solids content will increase by about 25%, so it'll double. The unit weight is also going to increase, and then our dewatering capacity will be about 45 acre-feet per year of biosolids to meet our 10-year timeline. First, we have to get the sludge from the lagoons into our drying beds. And for that, we're going to use a sludge dredge. Originally, we had thought we would be able to just let it flow by gravity, but there's not enough energy for that. And it also allows us a little bit more control over how the sludge is transferred. So we did end up including a lift station in our design because, like I said earlier, there's not enough energy to get the sludge from the lagoons to our drying beds just by gravity. Going to have a 64 cubic yard wet well, 2 submersible non-clog sewage pumps, and a valve vault just so we have a little bit more control, and its main purpose is to transfer the sludge from the lagoons to the drying beds. And then the drying beds themselves are very straightforward. Very simple technology. Basically, let the sludge be pumped into the drying beds and gravity will do the rest. It does allow for the sludge to be dewatered and reduce the volume with very low energy requirements and low maintenance. Our design includes 15 acres of drying beds. There's going to be 2 feet of sand on top of 3.5 feet of gravel. And then just a couple numbers, it's going to be 140,000 feet of drain tile, 11,000 feet of sewer, and 14,000 feet of force main. So this isn't going to be a small operation in any way, shape, or form. The hauling and drying schedule is also very important to our design. We estimate that it will take between 45 to 60 days to dry, and we're hoping for it to be pretty cyclical. So as soon as solids get taken off the drying bed, more biosolids, are being put on. For hauling, it's about a 6.2 mile round trip to the landfill. We can haul about 34 cubic yards per trip per truck, and that's based off of weight limits on the roads in the area. And we will need to do about 9 trips a day to make the 14,000 total trips possible in those 10 years. We also looked at the possibility of recovering nutrients from the filtrate that is generated in the sludge drying bed. There's lots of nitrogen and phosphorus in there, so it could be used as fertilizer and sold for profit. One example of this is struvite, which is widely used in the wastewater industry. We did have some concerns, however, most of which about the sludge being already partially digested. So it's already lost some of those nutrients. It's already been eaten by bacteria. And because of that, the cost of the equipment needed to recover the nutrients is going to be more than we would actually get from recovering the nutrients. So we're not recommending this option at the time. We also looked into how disposing of the biosolids in this way would be regulated, and they are regulated as the surface disposal of biosolids, and we also looked at some landfill considerations. So 40 CFR 258 is also going to be referenced. We also looked at how much daily cover the landfill actually uses, and we estimated about 26,000 cubic yards per year. So that will end up leaving about half the biosolids remaining after the decommissioning is complete, and they can either be used for later, they can be stored, or taken to another landfill. We also were concerned about disposing of the concentrate or filtrate generated because we won't be recovering the nutrients from it. They do have a higher nutrient content than typical wastewater, so slug loads on Fargo's wastewater facility was a concern. You don't want to upset their process. We analyzed BOD, orthophosphorus P, and ammonia concentrations. We estimated those off of data from Fargo's wastewater treatment facility and came up with the equivalent of adding 300 capita per day to Fargo's load, which actually is not all that many when you consider how many people Fargo's wastewater treatment facility serves. And it's also only about 0.1% of the average flow. And for these reasons, we decided it would be safe to just discharge the concentrate into the sanitary sewer system. This is just our final cost of the project. It's a little higher than we initially thought, but tipping fees are the biggest chunk of that, and that remained the same. Construction materials and cost take up most of the rest of that final total. Just a quick summary here. We did go with alternative 2, landfill, for our recommended solution. Our other alternatives were land application, incineration, heat drying and sales, and composting. Our process includes dewatering the sludge and then hauling it to Fargo's landfill where it will be used as daily cover. Thank you for taking the time to listen to our presentation. And please don't hesitate to email us with any questions or concerns you have. And yeah, that's all I got for you.